Good morning, all. Uh, in the module 1, we have come across the key enabling features of long-term evolutions. What are the basic structure, how the channel fading is occurring, how we are going to model that channels with different types, and what are the parameters we are going to analyze, and how we are making the ISI free communication link, all those things we have. And also the basic cellular concept, cell structure, sectoring, all those things. And followed by this we are discussing about in the module 2, that is multi-carrier modulation. So in the multi-carrier modulation, the first topic is multi-carrier concept. So this multi-carrier concept is used where it can be used already, where it is used, that we have to discuss. It is used in the DSL. The DSL is nothing but digital subscriber lines. Okay, mostly it will use in the telecommunication side, and also wireless LANs, that we can give the specification like 802.1 A slash G slash N. And also it multi-carrier concept is more popular in the wire digital video broadcasting, and beyond the 3G also, that is WiMAX, that is, and also long-term evolution. Here in the multi-carrier this one, the multi-carrier modulation has one common feature. Okay, common feature which will use the multiple parallel subcarrier, and this multiple parallel subcarrier will be generated by a discrete Fourier transform, that we will abbreviate it as DFT. And this common type of multi-carrier modulation, we will call it as OFDM, that is orthogonal frequency division multiplexing. If we go other example, we can see multi-tone, that is DMT, discrete multi-tone. The first we will see what is the purpose of this multi-carrier concept. Okay, to achieve high data rate and reduce the intersymbol interference. In the module 1, we have seen in the linear there is a intersymbol interference, and we have taken a lot of small attempts to reduce the intersymbol interference. And main thing for this multi-carrier concept is to uh, achieve the high data rate, as well as the reduce the intersymbol interference, which is represented by ISI. And this intersymbol interference symbol time is represented by TS, and this TS should be greater than the channel delay spread, and the channel delay spread is defined by tau. We know the channel parameters. Channel parameters are coherence time, Doppler spread, delay spread, coherence bandwidth, and angular spread. So these all are the channel parameters. So we have to correlate, or we have to maintain the certain parameters of the channel parameters. So here the time ISI symbol time, that is represented by TS, that should be greater than the delay spread tau, and the transmission bandwidth should be less than the coherence bandwidth. Then we will see the concept. Two main concept is the one is TS should be very greater than tau, that is nothing but the ISI symbol time should be very greater than the delay spread. So here this will, what it will do, it will divide the high rate transmission bit stream, okay, into capital L lower rate bit stream. The first step what we are going to do is we are dividing the high rate transmission bit stream into L lower rate bit stream. And what is L? And this L should be chosen in such a way that each of the subcarrier has TS into L should be very greater than tau, and it is ISI free, and the chosen L should satisfy these two conditions. And coming to the substreams, now we are dividing high into low with L types, and these individual substreams can then send over the L parallel subcarriers. So if you use the orthogonal frequency division multiplexing, obviously there will be a subcarriers, and here we have divided into L lower rate stream. So this can be sent to the L parallel subcarrier, and the desired rate should be maintained. Okay, whatever the desired rate we need to achieve, that should be maintained. If we coming to the second case, that is data rate on each subcarrier should be less than the total flat of the rate. Okay, total flat of the rate, and that is the second condition. And after the second condition, we are going to the elegant approach to inter-symbol interference. So first thing is achieving data rate, that is two conditions we are applying, that is the these two conditions we are going to apply. Followed by that, the next thing is the reduction of the inter-symbol interference. So what is the step we are going to, okay, that is the one effective approach we are going to take. Here we are dividing the wideband incoming data stream into L narrowband substream. Okay, na? We are dividing the wideband data stream into L narrowband substream, and this L narrowband substream which will be then transmitted over a different orthogonal frequency subcarrier. Okay. After that, these are the things we are going to take, and then the each symbol time Ts should be greater than the delay spread tau. Okay, so that will make the substream bandwidth will be less than the coherence bandwidth. So this ensures that substreams will not experience significant inter-symbol interference. And for this we will go illustration of multi-carrier transmitter and the receiver. So we will see the transmitter diagram. This is the transmitter diagram. In the transmitter diagram, what we are going to do, we are giving the input as R bits per second. So this R bits per second is nothing but the high data rate signal right here. See, if you see here, so the input of the transmitter is, that is a high rate data signal of the rate. That rate is nothing but R bits per second. And for this signal, the pass bandwidth is represented by capital B, which will broken into L pieces. So we are giving to the serial to parallel converter. In the serial to parallel converter, what we are, this pass bandwidth which will be broken into L, that is called parallel substream with data rate. The data rate is nothing but R by L. Okay, and B by L is nothing but the pass bandwidth. Now this R by L signal is given to the multiplier, that is this signal is modulated with cos 2 pi fc and then increasing with cos 2 pi fc plus delta f. Then the last signal it will come to cos of 2 pi fc plus L minus 1 into delta f. This is the way we are going to do the multi-carrier concept. Now all these signals are after passing to the channel. Passing to a channel, the channel is called represented by H of f. Right? Now these all are given to the adder, that is the signal with the rate of R by L bits per second will be get multiplied with cos 2 pi fc, then cos 2 pi fc plus 1 delta f, then 2 delta f, like that. All the signals are given to the summer. Then that summer will produce the output, that is x of t. Now if you see the receiver diagram, so what will happen, this x of t will be the input for the receiver. Let us see the diagram. This is the diagram given in this one. Then this received signal will appear without any subcarrier overlap under the condition. Here we are following the condition that B by L, that is should be very less than coherence bandwidth, which is represented by BC. So we can ensure that each subcarrier is with a flat fading. Therefore, the multi-carrier concept technique is possible or crossover there in the both time and the frequency domain. If we come to the time domain, see here, demodulation. So in receiver we are using a low pass filter. So why we need to use low pass filter? Here we wanted to use high quality low pass filter which used to maintain the orthogonality of the subcarrier. Okay, and also L independent RF units and the demodulation path. So here low pass filter should be chosen in a very carefully because this low pass filter is going to maintain the orthogonality of the subcarrier. Understood? So now coming to the time domain as well as the frequency domain. In the time domain, the symbol duration of each subcarrier, the symbol duration is represented by capital T, and the capital T is equal to capital L into Ts. That is the one condition. Next, the condition capital T should be greater than the tau, and this condition which will make that ISI free communication, that is capital T should be very greater than tau, which will make ISI free communication. And also in frequency domain, here we wanted to consider the subcarrier bandwidth. So that is represented by B by L. Here B by L should be very less than the coherence bandwidth. This condition will says that flat fading to the ISI free communication link. So that is the ensuring we are ensuring that the signal has obtained in a such a characteristic or such feature. So the time domain we are making that T is very greater than tau. That will ensure that is ISI free communication. And in the frequency domain, if B by L is very less than BC, that ensure that flat fading to ISI free communication. Such a way we have done through transmitter and receiver. This is the output graphical representation which we have obtained. So this is see here F1, F2, that is for first and F2, B by L. Okay, that is subcarrier bandwidth, and also that subcarrier bandwidth is very less than the coherence bandwidth, so that there is a flat fading, and we can say that there is a ISI free communication length. So this is the way we will get the output, and we are applying the multi-carrier concept to get the high data rate as well as the inter-symbol interference free communication. Hope you understood the multi-carrier concept by the illustration of the multi-carrier transmitter block as well as the receiver block and the output graphical representation. Thank you.